I'm guessing the reason makes you
All right, guys, let's get started. Well, Miss Smith? Not really. Good to put a face finally. All right, okay. Let me explain. I got a lot of explaining to do. I was a little bit sick actually. Not bad. There's something wrong with my nervous system, I guess. Too much work. You probably feel it, but I'm getting old. I guess that's the downside of that. You guys are probably fine. Immune system still working and everything, but mine's a little bit not full throttle, I guess. So I took time off and I see a doctor. So I might have to go into a physical therapy and things like that. So unfortunately, next week I had to go back to the area where I have the doctor that treats me. But nothing so bad since I'm still kicking alive, everything still high power, still drinking tea, switch to tea now, cannot do coffee anymore, apparently, too much coffee. I don't think that has anything to do with it, but trying to adapt, right? So I guess the age really caught up with me. Like my wife says, look fine, but you're actually 50 now. Not yet, right? 40, I guess. So the thing goes is that I know that you guys suffer from me being absent because of my sickness. So I'm trying to do more online presence to give you guys more help. And I think that from the exam, I've seen that a lot of information has been passed down. So I'm not so bad about it. I'm not feeling so bad about it, but there's a little bit bipolar in terms of the grading when I grade exams. And I promise you to finish that. I'm almost done. So I have like few people really, when I say few, quite a bit actually, around like 90s, 98, 7, 6, very good grades. And it seems honest and everything. And the process is legit. Everything is fine. I was very impressed. One guy actually don't usually come to class. He's not here today even, but he has his own way of studying. And actually he did very well. So I feel like this online format still works. Okay, so I feel like you guys actually watch the YouTube, read my lecture notes and really understand what's going on. So I feel like the overall approach is okay. But the other side of the aisle, I feel like a few of you guys start losing grip on the concepts. I see a lot of approaches were a little bit here and there, scattered, not really coherent. A lot of details were not figured out in the sense that a lot of it was just jumping and skipping. A lot of process seems like you don't have a good understanding, but you're right either way because that's what's showing the lecture notes, right? So let's try to do these things. I'm here this week. I'm gonna have an extra special session Friday, and I want to be here, and I want you to be here as well, hopefully. And when I say be here, meaning online or be in the classroom, doesn't matter. We'll figure out time, and then I will try to walk you through some basic examples. When I say examples, not exam examples, but some real cases that I have run into in terms of design, okay? And in the form of exam problems, so you guys can see better, okay? And also this is very critical. Now, rest of the lectures heavily relies on the shear design and also the column, right? That's the two components we'll be testing you guys. Some of the slab moment distribution, moment coefficient, which we'll talk about along the line, and those are important, but shear and column really important, okay? And I want you to have this experience that you know how to design flexure members. That means beam, the slab, and so on and so forth. We'll talk about slab after shear. And then you learn how to do shear. You learn how to do axial members for compression. Basically, at this point, after everything's done, you should be able to build a house yourself. No kidding, all right? Because you think about what is a house, right? Have columns, slab on top, and beams on top of it, and another column ramp up like that, right? So pretty much everything we learn are enough to cover a welcome, Andrew, was just talking about you. Oh, good job on the exam, by the way. So we were just thinking about you can do everything, right? Basically taking the knowledge you learn from this class, okay? And this becomes very useful, especially when you start doing senior design, all right? When you start playing with the software and everything like that, okay? So I think these are some things we can talk about this Friday as well. So in that spirit, I want to add one project, one course project, okay, to the course. And this won't be a very difficult project, some simple things, okay, but more in terms of parameter design, okay? And I will throw out a problem, work with you guys, and you guys will start playing the numbers yourself. And of course, we'll have the team competition, but this time everything will be done in virtual, meaning that you have your team meeting together and give me a best solution as you see fit, and weigh the results from each of your team and give you a corresponding grade. But like you know, for my class, I'm pretty nice, right? Participation is important, right? As long as you participate, there will be grade given to you for this. Okay, all right. So I think that's pretty much I want to say about overview of the course. And we'll talk about more tomorrow, Thursday afternoon, okay? We'll have course tomorrow, Thursday afternoon in person, I'll be here, okay? What I want to do tomorrow is go over some of the exam problems. And also I like to see you guys have any questions for me or anything like that, okay? You know, be prepared if you have something that's muddy. And I want to do this. I grade everything on the PDF, so I bring it with me tomorrow on my laptop. Now, if you have any grievance, I hope to release the grade tomorrow morning latest. I'm done grading most of them. Send the grade to the TA. He will upload to the Canvas system. Tomorrow morning, you should be able to see that before the class at least. Okay. And then if you have any grievance, problem, confusions, why, you know, I saw getting 90s, why getting 50s, that happens sometime, right? Maybe I added the number wrong, you know, come to see me and talk about it. Okay. All right. All right, so like I said, I don't want my small episodes affect your learning, and I try to put more time into the class in terms of online thing. But like you're saying, I'm fine, so I can take the workload. I just want to change the format a little bit to be more interactive. So let's do this as well. From next week, you know, when we're back to online, send me emails if you have any questions, okay? And I can hold one-on-one session to you for your studies. I did that with Andrew and somebody else as well. I think that worked. Okay, and I want you to think of it like a opportunity to communicate with me, right? I say this, but you don't probably follow it quite yet. I feel personally learning things is not the things that is difficult. It's the way you approach it can be challenging sometimes, right? You have to have your own way, but also have a systematic way to approach it. So I hope that I can teach you more than just the knowledge from this course. I can share some of my learning experience with you. Like you know that I'm pretty fast learner, right? I can probably learn everything in a very quick pace because I have a system. I think that works, right? You might have your own system, but some of the common features among the system can benefit you, right? I can give you a few examples. I have a few more minutes to spare here. So one example is that don't be afraid about a vast amount of knowledge you be tested on. Okay, with these days in life, right? How many courses you're taking? 6, 9, right? How many things you're running when you take a job, right? You have so many design, have so many people to interact. You have your families, you have your the other parts, right? You have a lot of things to worry about, isn't it? So the key is how to manage your information in a logic way and remember it in a fashion that when you need it, you can grab it. Okay, so you all know that memory relies on repetition, means that if you read something so many times enough, you can remember it, okay? My philosophy is that compartmentalize your memorized capabilities means that before study, for example, like a week before your study, right? Remember something, then go forget about it, okay? 2 days before the exam, open it up again, review it again, and right before exam, open it up again, review again. So it's like a fasting, right? You do intermittent fasting, you do intermittent memorizing, right? You don't go like full blown, then very night before, remember everything. So if you gave me 8 hours study, I will not spend whole 8 hours just studying the material. That's going to kill me. I'm not going to do that. I'll cut it into 4, 3, 1. So how to do that? 4 hours at the beginning, I take a very good 4-hour study. Do nothing, focus, coffee, tea, whatever you have it, right? Focus, no, nobody bother me, phone down, laptop down, just take a look at the notes, understanding things, right? No memorizing, no nothing, understanding things. Trying to understand why this guy write this way. There has to be a reason he write this way. There has to be a logic connection between the things he wrote, right? After that 4 hours, your understanding will reach a level that, oh, you understand things make sense. When you read it again, oh, these things become familiarized to you, right? They're familiar to you. And then the second 3 hours, try to memorize important equations, formulas, right? Understand how to use them, right? Say, oh, in my head, if I think about shear design, what are the critical equations? Start making tables out of it. Make tables, right? Organize them together in a creep sheet. That's the 3 hours for, okay? And then the last 1 hour, pretty much just go over it, quick review, right? Oh, if I have, do I still remember this? Oh, forgot? Should I refresh that? And that's not on your phone or app smartphone or smartwatch, whatever. So whatever I'm saying is not on there. What I'm saying is not on there, okay? So now you see that the last hour is very important because you may forget things, right? We all forgot things, right? So we can pick up the things you forgot. So do this systematic way, whatever you do, whatever you applies, okay? So don't get yourself swamped by information. Why I say this course is very like that. How many things were covered so far? A lot, isn't it? If you want to remember this in one get-go, that's impossible. That's impossible, okay? So you have to learn a compartmentalized way to learn it, okay? All right, now if you have any question about how to do that and how I do that, you can talk to me and we can have a little chat and maybe help you out, okay? But I feel like that's important. All right, and I think that's pretty much I want to say about this course so far, okay? Any questions, problems so far? Online access is okay, all right? So I upload everything on YouTube nowadays. Just go back, take a look at if we forgot something or I said something very ambiguous, you can play slow down like ambiguous, right? You can hear it clearly, okay? All right, so that's about it. Okay, so shear, right? Let's get back to the main content today, shear. What do we know about shear? About nothing, right? Your way, I'm asleep. You said something online, didn't have time to reach it, right? So what do we learn about shear? Two components, right, in terms of shear resistance. What are those two components? Concrete and steel, right? Stirrups, right? So there are two components, one from concrete. And what are the three components that are in the concrete part? Now look at this equation, right? VC equal to VA. A represent what? Aggregates. Y, CY, what is that? Compressed field, compressed region. And D represent what? Dow actions, right? So these three components give you the resistance from the concrete, shear resistance from concrete, okay? Remember this, why is that? There will be a multiple choice problem, right? Exam number 2 on this, final exam on this, right? So that is shear. Now, when we have the contribution for concrete, let's take a look at the contribution for stirrups, right? Stirrups, right? So we talk about the area of the stirrups and AV, and much about the yield strength of the stirrups, FYT. Let me ask you, if I have a stirrups just like this, and I say, this is number 4 bars, okay, what would be my AV? What would be my AV? First of all, what is the cross-section area for number 4 bars? Anyone? Area for number 4 bars. Anyone? 0.2 inch squared. Perfect, right? So how about AV then? 0.4, right? So 2 times 0.2, and that is 0.4 inch squared. Great, right? What if I have a stirrups, okay? What if I have a stirrup? You may think I'm joking, but I'm not, okay? If I have a stirrup like this, oh, wrong side. Okay, yeah, to give you the full picture. There's another one outside, another one outside. And this is actually a real column in Fukushima, but anyway. How many, well, what is AV here? If all these are number 4, what is my AV here? Got a 1 point, I got a 0.4. Do I get a second guess? 2.4, why is that? There's 12, right? So it's just like a crab, right? Just like crab. How many legs I have? How many legs I have? Let's do a count, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, that's it. That's it. So that depends how many legs that across the section I'm cutting, right? What if in the corner, like I have a Star Wars warehouse, right? So I mean Tesla, right? I want everything looks just beautiful, right? Why? I don't know. Maybe I just want more money out of it. But anyway, so I have a Star Wars like this, right? Now, what will be my AV? What would be my AV? 0.4 still, right? Why is that? Why is that? Okay, another rule, right? You think of it, it is a column, isn't it? It is a column, right? So meaning that I have a column look like this. And when I do the shear diagram of the column, right? So my V can come this way, my V can come this way, and my V can come any other way, right? So really depends on what is my shear force direction, right? And you drew a perpendicular line, to that shear force direction. And how many legs it cut through give you the cross-section area. Get it? Right, so that's the two principles. One, depends on how many legs across the section. B, the sections depend on which is the perpendicular direction of the shear force that being applied. Okay, being applied. So this is very critical. Okay, this is very critical. Now, if I have a beam like this, a double helix column, right? Double helix, and I built this column before myself, right? Double helix column, and have stirrups just like that. Okay, in the cross-section view, right? This is all hidden in the oval shape of a column, all hidden like that. Now, all these are number 4 bars, of course. And what would be my AV? 1.6. How you get that number? 1, 2, 3, 4. 4 multiply 0.2. Oh, that's not 1.6, is that? I don't know. That seems like 0.8, right? That's okay. That's okay, right? So what's the other number? Is this the number you like? Is this the correct number? What is the answer here? It depends, right? Why it depends? Why it depends? Look at the column, right? It's oval column, has 2 directions. Oval means like eclipse, right? Eclipse. Not speaking English for a while now. Eclipse, right? So 2 axes, right? A, the long axis, B, short axis. Really depends on which direction the shear coming from. If the shear coming from this way, right? You're using the strong axis, right? The weak axis, right? The flat one, right? Bending this way. And then you cut this way, right? Cut 1, 2, 3, 4. 4 of them, right? So 0.8 inch square. If your shear force come from this direction, right? How many legs you cut? How many legs you cut? Depends again, right? Where do I cut? Do I cut here? Do I cut here? Do I cut here? You cut, now be careful now, you cut the least number of legs this cross section is gonna have, okay? Least. So now let's take a look at this, right? So 1, 2, 1, 2, like these 2 cuts the same thing. So if I cut from this direction, AV equal to 2 multiplied by 0.2, that is what? 0.4 inch squared. Get it? And to put it more systematic way, usually you give axis, right? So this is x-axis and this is y-axis, and this will call it, this direction is this way. So this is Vy direction and this is Vx direction. Okay. All right. So I want you to understand that this depends on loading conditions. Okay. All right. Okay. So that's about the area, right? So once we have the steel, things are clear. Now AVFYT give you the resistance from the steel and they add up together. So the total shear resistance have 2 parts, concrete part and steel parts. And now you have to consider the stress reduction factor, right? Of course, phi is our stress reduction factor. And for shear, what is phi? Phi equal to 0.75, okay? 0.75. And what is the difference between this phi and the phi in the flexure members, in the bending, in the moment? Now, the other one is dependent on what? Epsilon T, right? This one is what? It's constant, isn't it? 0.75 always, right? So with that, we move on. We say now, okay, just estimate the shear resistance from this equation U, that is applied shear, divided by phi, which is stress reduction factor, minus VC, concrete contribution, and you get a shear force from the steel, shear resistance from steel, okay? And what is contribution from concrete? You have this fitting, which means you do a bunch of experiments trying to fit the data. You threw a line, and that lines give you the equation, the empirical design equation here, square root of prime C, BW ds, then lambda. Lambda is the weight coefficient, right? Normal weight 1.0, lightweight 0.75. All right, BW, a little bit different, right? Have to find the narrowest width across any section here. So that's what we talk about. And ds, when you don't know ds, when you do design, when you don't have ds yet, estimate 0.8 h. Estimate 0.8 h. You have to have the section dimension, which is h here. But you don't necessarily have to know where the flexure bars are to give you the shear design, okay? So if someone comes to you and say, Bob, I want you to design shear for this member, you say, do I need to know the flexure or not? You don't need the flexure. You can design for shear straight up, all right? You don't have to know the flexure to do shear, okay? They don't go sequence. They are in parallel. All right, so once you have that, you plug in this equation, you estimate what is the stirrups contribution, right? And you use this equation AVFYT ds divided by s to find out the spacing. Why is that? In the shear design, stirrup size number 3 and number 4 usually given, not much of a choice, right? All you have to do is design spacing, distance between the stirrups, okay? distance between the stirrups. All right, so that's pretty much what we learned, right? And then we have this nice equation here, right? Nice equation here, just like I said, how to remember things, right? So we understand why, and you have summarized everything here. Take a look at them. Now I can probably memorize them, right? So first equation for concrete, second equation for different stirrups. One's vertical, the other's inclined. But be careful, we don't do incline in this course, right? Be smart about it. Don't need to worry about it, right? No sine alpha, cosine alpha, probably multiple choice, and not even that probably, right? So just the vertical stirrups. This equation is important. Once you have that, you have Vn equal to Vc plus Vs. You have this equation, and you verify your design process, just like that. All right. But it says easier than done, right? ACI says you have to have a lot of limitations, constraints, minimum amount of reinforcement. These two equations, right? These two equations, and it has to be the largest of these two. Largest of these two. You say, Bob, you're confusing. The other set of equation, you say the least of them. Why? Because if you're talking about the minimum area, it's the larger of these two. If you're talking about the maximum spacing, it is a list of them too, right? They are inversely proportional, right? They're inversely proportional. Be careful, okay? And we'll talk about them, right? And then after everything said and done, finally, we have our design equation for spacing between stirrups. S required equal to this bunch, okay? Top AVFYT ds divided by VU over phi minus VC. This is pretty much the shear resistance required for stirrups, and so on and so forth. And this is the special requirement, and that is in the 45-degree diagonal cut, right? At least have one stirrup present, okay? And also have other requirements. If the shear resistance exceeds 4 times this, change your spacing by half, okay? And now this becomes a little bit longsome. So we made an equation here, made this little table here, right? VU smaller than equal to phi Vn. And then you have this resistance for shear, and then required spacing, max spacing, and this max spacing, and this max spacing, and then this, and this. You are so confused, isn't it? I will be, right? So many things. Now, at this point, you say, no, I cannot do this. I have to make myself a table. All right. So before I go back to the example problem, right? I want to make a table for you. Okay, we'll resume all this. Don't worry, but we'll resume this, right? So with all these equations, I now understand where they come from, but I don't necessarily understand what's the relationship among them. I don't necessarily want to remember them in this way. So I will make myself a table, organize them, and memorize them. How do I make a table? I took a look at things. I realized that it's just 2 criteria I have to play here. So number 1 criterion is that when phi VC divided by 2 is greater than or equal to VU. All right. So what does it mean? It means that half of the concrete resistance is already satisfied or already bigger than the required shear, meaning you probably don't need any stirrups. Okay. You don't need stirrups because the concrete alone, half of it cover it. So why you need the stirrups, right? So that's one condition. The second condition is that phi VC divided by 2 is smaller than VU, right? So the concrete itself does not cover it, but phi VC itself, right? Half of it does not cover it, but phi VC itself still covers it. Okay, that's the second condition. Now the third condition, that is phi VC, concrete itself cannot cover it, but the required shear from the stirrups is smaller than 4 times square root of prime C BWD. Okay, that's the third criteria, isn't it? So it depends on whether my concrete can cover it or not. Now the last one is that my VS required shear is greater than 4 times square root of prime C BWD, but is smaller than 8 times square root of prime C BWD. So what I just did is I categorize them. I logically categorize them, divide them into columns, so I can understand what are the other equation, how the other equation fall in places, right? So now I made the table for myself in nice 4 columns, right? And I want to list all my equations into this column. So with these conditions, what are we doing? We're designing for design table for what? For stirrups, right? Stirrups, 2 things: area, not control. But the other thing, what is it? Spacing between the stirrups are in our hand, right? So we're essentially designing for spacing S. Okay, and to be more precise, we are designing for what? The maximum spacing allowed to arrange the stairs, right? You pretty much can put stairs any space you want. If you want to put it, I can put like 1 inch apart of stair just enough to get aggregate through it. And that should withstand any shear I want, right? But you don't have to do that because there's a maximum spacing to give you so you can what? Reduce the cost to put less stirrups in it, isn't it? So that is what we're designing for. Now understand that, then the following equation becomes, all these are as max. Okay, all these are for as max. So out of these 4 conditions, the first one, when this happens, the half of the concrete resistance is already covering the shear. I only need to provide the spacing, and let me just use this color back. FYT, AV, and then divided by a 0.75 square root F prime C BWD. And immediately you realize that this comes from the minimum shear reinforcement requirement equations, isn't it? I just manipulated and made this way. Now the other one, of course, is another equation, right? Same thing, AVFYT divided by 50 BW. That's it. So that means if I fall into this category, I just need to compare these two, find out least or larger one or lesser one. These two, larger one or lesser one. Least, right? Lesser one, right? Smaller one. Why is that? Why is that? Let me ask you this. If I were to design for shear, right? Which way is more conservative? To put the stairs closer or to put the stairs farther? Closer, isn't it? So of course, the maximum spacing has to be the lesser, right? Lesser of the two, right? So put a minimum sign here, okay? Minimum of these two. Right? Always apply for all of the smallest number for all the spacing, right? To be safe. Now, for the second category, when half of PVC smaller than VU, but PVC itself, the concrete itself covers VU, right? Now you have 24-inch and D divided by 2. What is the depth of the section, right? And then these two, right? Just copy these two down, AVFYT divided by 0.75 square root F prime C BWD, and then AVFYT divided by 50 BW. All right. Now move on to the next category. Now we say that when your required shear for stirrups has not exceeded the 4 times this, everything remains the same. So 24 inches and D divided by 2, and then AVFYT, I'm just copying these two equations, 0.75 square root F prime C BWD, AVFYT divided by 50 BW. Right? Not much of change, right? Because it hasn't exceeded 4 times of square root F prime C BWD, right? Right? But is that it? Knowing me so long, you know it's not it, right? What am I missing here? What am I missing here? Now, you think of it, right? The previous 2 categories, we're talking about what? We're talking about the concrete itself has already covered the required shear. Meaning what? The stirrups are just there to help, but not really helping much. I don't need that. I don't require stirrups to be there, just to be there to be safe, isn't it? For our peace of mind, that's it. Nothing much, right? But this is pretty much a division line here, right? So on the left, no VS calculation needed. I don't need to calculate how much shear contribution from the reinforcement at all. I don't care. I put all these equations down. All the equations, nothing to do with applied shear, nothing to do with the stirrups, basically, right? Minimum reinforcement requirement. That's it. ACI says so, so I have to put there, right? Now, if I move to these 2 categories, I realize that I need to calculate the required shear now, isn't it? Why? Because concrete itself cannot do it anymore, isn't it? Concrete itself cannot do it anymore. So this right here has to be as required. And what is the equation for as required? You remember it? Do you remember it? Come on, help me out here. What is the equation for that? Required spacing. AVFYT. Always start with AVFYT on the top, right? And then DS, then? Right, so that is VS, right? That is VS, right? So what is VS? VS equal to VU divided by phi minus VC. And what is VC here? VC is that 2 lambda square root M prime C BW DS. See? Box it. Got to do the calculation now. Cannot be lazy anymore. Got to do calculations now, right? So that is added elements in category 3. Okay. All right. So moving on from category 3 to category 4, right? Pretty much the same. Only thing changes VS is greater than 4 times square root F prime C BWD, right? So I need a whole lot of shear from the stirrups. And when you do that, ACI says, well, folks, be careful. You got half your spacing, right? Half your spacing, meaning 24-inch requirement become 12, and half of D requirement become D divided by 4. This is called spacing half, just to be safe, just to be safe. Okay, got it? All right, so that's the change. Then the rest of the thing stays, right? Rest of the thing stays. So AVFYT, let me just use this color here to show you that it hasn't changed. AVFT, 0.75, square root F prime C BWD, AVFYT, 50 BW. And this fellow here requires stay, so I'm just going to use the first part equation. You can use the rest, and that is this fellow right here. Okay, sorry, typo, VS. Okay, and what is VS? Use this equation, right? So now this is the 3-hour thing I was talking about, right? Once you made the creep sheet, you can now take a look at it and remember it just like that. All right, okay, so this is clear than what we just talked about last time, right? This is more clear. This is more table organized stuff. So you need to make creep sheet like that. See, the creep sheet doesn't matter. The process of making it is very important because you organize stuff, right? Understand it, and you can link them, and you can sort them out and remember easily. Okay, so making creep sheet is important for you. Okay, making creep sheet is important for you. Okay, all right. Now with this, I'm pretty powerful. I feel pretty good. Now I can handle all the things I want to handle. So I go back to the example problem. Take a look at it, right? So these are the problem. So now you see the problem, you realize, Bob, now I understand it. You're very cunning, right? You're very smart, right? You program this problem like that. What I'm doing here. So you think of it, right? So basically just like the table, right? First category, this is what? First category, this is what? Half of PVC covers the required shear. This is probably the first category, right? See, I'm manipulating things. I just want to show you, right? Second category, PVC itself covers the shear, isn't it? Third category, right? Less than 4 times the square root of prime C, BWDS, right? Smaller than that. This is what? Bigger than 4 times, smaller than 8 times. This is what? 8 times. Do you see it? Right. So I'm not smart. I'm just like you, right? But I know more, so I make it look like I'm smart. I'm not. You know, right? How the game's played, isn't it? Okay, see it, right? So that's how we play. So where we at, right? So we talk about this problem, done. We talk about this problem, and let's take a look at C equal to 54 kips. C equal to 54 kips. Okay, so how about it, right? So let me show you. Now C equal to 54 kips. VC equal to 50. VU equal to 54 kips. That means number C here, VU apply shear, that is 54 kips of force. Now VVC and VVC stay the same because section stay the same, right? We haven't changed the section yet, and that is 24.5 kips, which is smaller than the applied shear, which is 54 kips. Smaller than the applied shear, which is 54 kips. All right. So in this case, you say stirrups needed. And well, we're at it, right? Which category this one is? Which category this one is? Take a look. Definitely not this. Definitely not this. Is that this? Might be, isn't it? Might be, right? Is that this? Might be, right? What is the difference? 4 times of this, right? 4 times of this, right? I need to check that. So now I think of it, hold a minute, wait a minute. Let me do that, right? Before I do everything else, let me just check that. So 4 times of square root F prime C BWD. I know how to use that, so might as well put it here, right? So what is this? 4 times 4,000 PSI of the concrete, and then multiply BW. What is my BW here? 12 inch, isn't it? 12 inch. And what is my depth here? 21.5 inch. Now I didn't really have this number out. Please help me. Help me. Can you pull out your calculator and get this number out for me, please? Come on, help me out here. 65. You read my notes? 65. Right, that's right. 65.3 kips. How did he know that so fast? How did you know that too fast? So fast. What is this? This is what? 2 times 2 square root f prime c bw d. You ruined the surprise, by the way. Very smart. And that is what? That is what? That's what? V C, isn't it? VC. Okay. Good. So that's where it comes from, right? Simple, right? And nothing difficult. Why the world is complicated to you? Because counting people like me try to pile all the details in a special way that confuses you. All right. But if you understand the bottom, the fundamental things, right? Things are very simple. Nothing is complicated. Under the sun, nothing is new. All right. Okay, good. Now take a look at this, right? So I can immediately say that I don't have to do the calculation. I say 2 times of VC, and I calculate VC before, and this is 65.3 kips. All right. So once I have that, right, I take a look at what I need, right? So what is my VS here? Let me use back my black color. VS required shear for stirrups equal to VU divided by phi minus VC, and that is 54 kips now, divided by phi 0.75 minus VC, which is 32.6 kips. And then I have, let's save the trouble, 39.3 kips. When you see this number, you are smiling because this is smaller than 65.3 kips, and that is way under the 4 times limits, right? 4 times limits. So when you say that, which categories are we in? Which category? 1, 2, 3, 4. Which one? Category 3. All right. So right, you have a table, right? Use it, right? Have a table. Category 3. So other equations. What other equation I need to use? I need to check all the equations, right? So I just put these equations in my solution sheet and solve it, just like that. Okay. All right. Simple, right? So now let's take a look at this. So okay, with this, I know this is what it is. So these equations are S max has to be the least highest requirement, right? Then let's list all these equations, right? 24 inches, fine. DS divided by 2, 21.5 inch divided by 2, what is it? What is it? 21.5 divided by 2, what is it? Come on, we calculated this before. 10.75, great, thank you so much. And then AV FYT divided by 0.75 square root f prime c BWD. What is this? What is this? Let's write it out, right? What is AV? 0.22 inch squared, right? And what is FYT? 60 KSI, right? Divided by 0.75 and multiply by square root of 4,000. Okay, and then, oh, sorry, clear this out. And then BW 12 inch and DS 21.5. Can I get this number on it? We did this before. You can see from the previous notes. What is it? 20. 3.2 inches. We did it before from last lecture, okay? All right, so now with that, AVFYT divided by 50 BW, and same thing, 0.22 inch squared, multiply a 60 KSI, divided by 50, multiply 12 inch. And you should have this number of 22 inches. Okay, all right, that is these 4, right? But go back to the category, right? Category 3. I have to calculate as required, right? So as required is an added item here. So to do that, AVFYT DS over VS, right? So AVFYT 0.22 inch squared, 21.5 inch divided by VS. What is required here? Let me go back, take a look, right? So that is 39.3 kips. So 39.3 multiply 1,000. Okay, multiply 1,000, and you multiply 1,000 on top to make a PSI, or you can do this and you can do this. Okay, it really depends on you. Because top is KSI inches square, bottom is kips. Okay, all right. So I really don't have this number mapped out. Please help me. 0.22 multiplied by 21.5 multiplied by 60 divided by 39.3. Let's try it. Let's try it. See what you get. 0.22 multiplied 21.5. Multiply 60 divided by 39.3. Okay. How much you have? 7.22 Do I get the same? Do I get a second? Yeah, yeah, yeah. All right. Okay, I got 7.26, but that's fine. Okay, let's go with 2.2. Okay. All right. So 7.22 inch. Yeah.
Are we supposed to be using?
Oh yeah. Did I do wrong? Yeah, I did. No, no, no. We're using this one.
What are we supposed to be putting in 60 or 60,000?
It's a 60 KSI, right? It's a yield strength FIT 60 KSI, right? So the bottom here I switch back to kips. The top here I have inch squared, inch, right? So check the unit. That's a good question. Let's do it, right? So top, what is the unit here? Inch squared multiply inch multiply KSI, right? What is KSI? Kips per inch squared, isn't it? So after this, what kind of unit I got? Kips inch. Okay, bottom here, what I have? Bottom here, what I have? Kips. So kips cancel the kips. I should have what? Inch. Does that make sense?
Yeah,
You got a different number?
only on the 23.2 one. I didn't get.
This one? Yeah. So there I made a mistake. So here you have to multiply 1,000. You're right. My apologies. That's where I think I made a mistake here. Does that make sense now? Yeah, this is different, right? The bottom here is a PSI inside, right? Here is 50 actually has a PSI, but anyway, it doesn't matter. The top has to multiply 1,000 PSI.
I'm still getting a weird number.
Still getting a weird number?
Yeah.
Okay. Okay, let me try this. How about take this one out? Do you get the same thing or different? Maybe just my typo. Do you get the same or different? Try it again. You got the same, right? So I made a typo. DS should be removed, okay? Sometimes I slip things, okay?
Is there
No DS, no DS, right? Okay, right. So let's check the unit, right? Sometime I made typo, right? It's been so long, but let's check the unit, right? Just make sure we're safe. So AV is inch squared. So on the top, this is inch squared multiply KSI. So I get KSI inch squared, I get a kips, 1,000 pounds, right? Bottom here, I have BW, which is inch. And square root of F prime C should be PSI, right? So PSI, right? So let's just say PSI, pound per inch, PSI inch squared. Okay, so this fellow here gives me pound divided by inch. Is that right? Is that right? Yeah, I think so. I think so. Yeah, the unit is somewhere messed up, right? Unit messed up. Okay, let me put a pin here. Let me go back and check the unit, okay? I promise you I'll get back to you tomorrow, okay? Check unit. I think something's messing up here. Okay. All right, let me get back on this to you tomorrow, okay? Haven't done this for a while now. Sorry about that. Okay. Anyhow, so do you get the 23.2 now, Natalie? Okay, you're good. All right. So now this is the correct number, 23.2 inches. Okay. Now, out of these 1, 2, 3, 4, 5, let me put them out. 1, 2, 3, 4, 5. Out of these 5 numbers, which one is our S max? 7.22 inch. So this one governs. Okay. Yeah.
So is the D that we put in the table we just created?
Yeah, let me remove that. That is wrong. Okay, folks. Sorry, horrible mistake. Okay, horrible mistake. Yeah, let's clean it up. Yeah, I didn't have it here. Just today, I think I remember it wrong. Apologize. Okay, apologies. Okay, all right. I think that's the last place, but let me know if you find more. Okay, sorry. Like I said, nervous system, right? Gone haywire today. Anyway, so S max equal to 7.22 inch square governs. That's the base numbers. All right. What does that mean? What does that mean? It means that I need to put my stirrups within 7 inches among each other, right? You go tell Joe, Bob on the field, say, put the stirrup 7 inches apart from each other, what do you expect me to do? Well, I don't know, but I will chew my tobacco and say, sure. Right? And I just put them what? I don't know, half a foot, because 6 inch is easier, isn't it? Right. Why? 7 inches is a strange number. Nobody will build a jig for 7 inches, isn't it? So at this point, I would just tell my constructors, look, fine, if you want to put 6 inches, put 6 inches. That's good for me, isn't it? So I will go with design. I say now, design for number 3 stirrups at 6 inch. Be done with it. Okay. Get it? All right, good deal. So that's how that is done. Okay, that is how it's done. All right, so moving on, right? Now with that, I say D, VU, bump up a level, 77 kips. VU, 77 kips. Okay, I know from the story how it's engineered. This is probably going to be category 4, right? This is probably going to be category 4. I know that it's coming, right? But I still need to check that. So 77 kips, apply shear. That is bigger than VVC, right? VVC is 0.75 multiply. What is VC again? Let me just double check. 39.3 or 72.6, 32.6 kips. So that, ladies and gentlemen, is 24.5 kips. So VU has to be bigger than that, and VS required is VU over phi minus VC. So we have this done before, and this is 70 kips. Oh, no, I have done this before, right? Let's just do it. So 77 kips divided by a 7.5, 0.75, then 24, so 32.6 kips. This is this number right here, and I have this number to be 70 kips. Okay, save you the hustle. Okay, so that's that. And don't forget, right? Don't forget, we are at a critical point here. We're at category 3 and we're bumping into category 4. We're bumping into category 4. And how do we know we are in category 4? What did we do in the category 3 in the problem C there? We check with 2 things, right? So this VS required, I want to see if it's 4 times square root of prime C BWD, or I want to also see that whether it's under 8 times square root of prime C BWD. Okay, so what is this? This is what? 2 VC, right? VC is what? 32.6. So 2 VC is what? 65.3, right? 65.3. So 65.3 kips. And then smaller than 70 kips. Fine. That satisfied. And how about 8 times? 8 times basically 2 times of 65.3. So that is what? 6, 0, 13. Is that right? Is that right? I just did that on the fly. Is that right? I'm not so comfortable with my own. Okay, good, good. So that is it. So now we're officially in category 4, column 4. Remember that tiny table there? Fine. Okay, so I'm happy. Okay, so now I'm going to go back to the table right here and take a look at the equation, right? Take a look at the equation. So 12 inch, because it's half D divided by 4, and this blah, 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 right? Blah, blah, blah. We did this, right? Now take a look. So now as spacing, as max has to be least of, right? So first 12 inch, fine. D divided by 4. What is D divided by 4? What is D divided by 4? 21.5 divided by 4 is what? It's 10.75 divided by 2, right? What is 10.75 divided by 2? 5.375 inch. All right, something like that, right? So what are the other 3, right? AVFYT divided by 0.75 square root F prime C and BW. Sorry, again, maybe say 22.3 inch AVFYT divided by 50 BW. I did this before, just out of memory, 22 inches. And also AVFYT DS over S VS, and that is 7.22 inches. Okay. All right, now out of these 1, 2, 3, 4, 5, which one governs? .37, but I made a mistake, did I? I made a mistake. Where did I make a mistake?
The VS.
The VS changes. Okay. So when you copy the equations, right? I made this mistake all the time. So when you copy the equations, right, be mindful something actually are changing, right? Something actually changing. So this number is not correct. Okay. So unfortunately, you have to redo this number. So let's take a look. So 0.22 inch squared and multiply 60 KSI multiply DS 21.5 inch divided by VS. What is VS? 70 kips. Is it 70? Yes, 70 kips. All right. Can you help me out here? Can you help me out here? Type in what you have, 0.22, 60, 21.5 divided by 70. How much you're getting? 4.05. Second? Comfortable? Good. All right. Now, all this. Take a look at it again. Which one governs? Which one governs? 4.05 governs. All right. Now, Bob on the field, you guys call me, right? Bob, we have this number down. Go put the steroids on it, right? What am I spacing? I don't know. What am I spacing? Tell me. Which one to go? 4 inches, right? Why? Because 4.5, let's round that 4 inches. Sure, but why 4 inches particularly? Because 4 inches is a good number, right? A foot, I put 3 stirrups. So that's how I like it. You realize that on the field, your number don't matter. As long as they keep it under your number, they're happy. Okay. So when you do design, try and have that sense in your design, right? So what are a good spacing? 2 inches, tightest. 3 inches, because you can put 4. 4 inches, you can put 3. Then don't go 5, jump to 6. Get it? Jump to 6. Then 8. Why 8? Because I can put double 4 inches spacing easily. Why? In the field, I have a gauge, right? I can measure it. Right? Okay, good. Class dismissed and see you on tomorrow, right? Be sure. I'll send the email about Friday meeting and we can set up a time. Okay, if it's too late, we do online, don't worry. And always be recorded. You can view them later as well. Okay, but I encourage you to participate. So we have a more dialogue that way.